But see what happens when we add unequal weight to the ends of the balance bar. The 3-pound weight on the left creates an unequal force that overcomes the 1-pound weight on the right. The unequal force at the ends of the bar is transferred to the shaft in the middle, causing it to twist.
This twisting force is called torque, a term that may be new to you. Torque is the amount of twist that's applied to a shaft. It's measured by multiplying the force that's imposed at the end of a lever by the length of the lever arm. With our unbalanced teeter-totter, we see that the counterclockwise torque on the shaft at the left is greater than the clockwise torque on the right. So the difference in torque causes the shaft to twist. How can we balance the torque given these unequal weights? Remember how you balanced a teeter-totter on the playground when your friend was heavier or lighter? As on a teeter-totter, we can move the heavier weight closer to the axle to balance the torque.
If we now move the 3-pound weight in to a point 1 foot from the center axle shaft, the bar again comes into perfect balance. The clockwise and counterclockwise torques on the center axle shaft are equal, since the small 1-pound force at the long end of the balance bar is now multiplied by a 3-foot length or lever arm, while the 3-pound force at the other end is multiplied by only a 1-foot length.
It's now clear how we can lift a heavy weight using only a small force. We just need to use a short lever arm for the weight and a long lever arm for our force. The ancient Greek mathematician Archimedes said that with a long enough lever arm, he could move the earth. Such a lever arm would have to be extremely long to generate the tremendous torque required. Keeping in mind that torque is a force times a lever arm, we'll now see how gears can increase torque just as levers do. Think of each tooth on a gear as representing the end of a lever arm that extends from the center of the gear to the tooth. In this example, with the 2 gears fastened together on a single shaft, the lever arm of each gear is its radius. In the case of gears, the forces at the ends of these lever arms are called rim forces. Just as with the balance bar example, the clockwise and counterclockwise torques on the center axle shaft are equal, since the small 1-pound rim force on the large gear is multiplied by the large gear radius, while the 3-pound rim force on the small gear is multiplied by the small gear radius. While the 2 torques are equal, the ratio of the rim forces is exactly equal to the gear ratio. This works the same way in meshing gears. Now, to demonstrate how torque is multiplied by meshing gears, we'll use this 3-to-1 ratio as our example. If we place a small weight hanging from the teeth on the left side of the small driver gear, it will produce an equal upward force at the point where the 2 gears mesh. This upward force, in turn, can be balanced by an equal downward force applied to the teeth of the large driven gear, and the gears will remain stationary. However, the torque in the small gear shaft is balanced by a torque 3 times as big in the large gear shaft, because the lever arm or radius of this gear is 3 times longer than that of the smaller gear. The same formula also applies to gear trains. Whether it's a simple set of 2 gears or a compound gear train, such as this 18-to-1 example made up of several gears, the torque is always multiplied by the overall gear ratio. In this case, the torque in the last driven shaft is 18 times larger than the torque in the driver shaft. Therefore, if the last driven shaft has a gear attached to it with the same lever arm as the driver gear, that is, the small red gear in this example, then the rim force will be 18 times larger. What we've discussed about lever arms, rim force, and torque can be reviewed by referring to the page numbers now on the screen in the Teacher's Manual for the World in Motion 2, Challenge 2. The things we learned about how torque and speed work with gears can also be applied to wheels and how they work. A wheel also has a rim force and a lever arm that corresponds to its radius, and the torque in its axle is again measured by multiplying the rim force by the lever arm. First, to demonstrate a practical application of what we've learned about torque, here we see two wheels. One is 3 times larger than the other. In this example, the wheels will drag equal-sized weights. In order to pull the weights, the rim of each wheel must push back against the ground with enough force to overcome the drag of the weight. Let's imagine that both wheels are connected to gear trains which equally apply 1 unit of torque to the axle of each wheel. The small wheel can pull the weight because the force exerted by the rim of the wheel on the ground is enough to overcome the drag of the weight. But with the same torque applied to the larger wheel, because of its 3 times greater size, it has only 1/3 the force at its rim and cannot pull the weight. The large wheel needs 3 times the torque to pull the same weight. When 3 units of torque are applied to both wheels, the smaller wheel is able to pull 3 times more weight than the larger wheel. A good example of this can be seen in bicycles. If 2 bicycles have the same sized gears but different sized wheels, the one with the smaller wheels will be able to climb hills or tow a load with less effort than the one with the larger wheels. Here's another comparison between the same 2 wheels. In one complete revolution, the small wheel will travel only 1/3 as far as the large wheel, because it's only 1/3 the size. In one revolution, each wheel will travel only the distance equal to its circumference. And if both wheels are turning at the same number of revolutions per minute, the large wheel will travel 3 times faster than the small wheel. This effect of wheel size on the distance and speed a wheel travels is a subject of experiments found in the teacher's manual for the World in Motion 2 Challenge 2 on the pages listed on the screen. Combining the 2 effects of wheel size on torque and speed that we've discussed, we see that when 2 wheels of different sizes are attached to equal-sized gears driven with the same torque and speed, the larger wheel will travel across the ground faster than the smaller wheel, but will not be able to pull as heavy a load because the force at the rim is less. The 2 effects are opposite. A bicycle with large wheels can be ridden much faster than one with small wheels because it travels further with each wheel revolution. But the bike with small wheels can more easily climb hills because the force at the rim of its back wheel is greater. Now that we've seen how gears and wheels work, let's look at some of the ways this knowledge is used in the real world. Most electric motors and engines turn at thousands of revolutions per minute, which is much too fast for most applications. By using gears as we've shown, the high rotation speed of a motor or engine shaft can be smoothly reduced to the slower speeds necessary to drive the wheels of a car. This is what a car's transmission does. Higher gear ratios provide the high torque required for acceleration, but lower speed. Lower gear ratios provide higher speed, but lower torque. In these examples, we've seen that in any gear train, the speed of rotation is reduced by the gear ratio, and the torque is multiplied by the gear ratio. The 2 are always inversely related. If for some application, such as an egg beater, you needed a very high speed with low torque, you could simply reverse the gear train and make the large gear your driver. In this example, you would attach the motor or power source to the large blue gear on the left, making it the driver gear, and the small red gear on the right would become the driven gear, rotating 3 times faster than the driver gear. By simply adding more compound gear pairs, even higher speeds than this can be attained. Gears and wheels are very handy devices. Gears can change the direction of rotation of shafts. They can increase or decrease the speed of rotation or the force exerted at their rims. Wheels can be made to travel fast or slowly across the ground, and can be made to push hard or easily against the ground. With all these possibilities, engineers can design tractors or race cars, clocks and watches, Ferris wheels and rotating restaurants, airplane propellers, and thousands of other useful things that constantly keep our world in motion.